Good morning, everyone, and welcome to today's Tech Talk on Solid Edge Engineering Reference and Catalog parts. The engineering reference is available with every version of Solid Edge. This can be accessed from the Tools tab in the Environment group, then by selecting the engineering reference. Once you select the engineering reference, this gets attached to your right side edge bar, and then you can see a bunch of different types of parts that you can generate. Some of the examples are shaft, cam, spur gear, bevel gear, worm gear, pulleys, beams, columns, and so on. So here we are just going to take a look at an example of what exactly is the workflow to generate one of the standard parts here. So here I'm taking an example of spur gear, and most of the other standard parts can be generated with the same workflow. So this is divided into three separate sections. First is the design parameters. So this is used to input the parameters of design and strength calculations of a spur gear. The options here is used to access the input conditions and select the type of gear and method of calculation for strength check. And then you can assign the material in this specific case to the pinion and the gear from the list of materials available inside the design parameters. So once you have specified all of the values such as center distance, the desired gear ratio, the pressure angle, the helix angle, the hole diameter, face width, and all of the parameters for both the pinion and the gear, you can select the calculate option at the bottom. And this takes you to the next part that is called as a calculated results. So here this displays a general result for gear and pinion and overall performance in terms whether the gear and pinion that you're trying to generate has passed or failed. So the results generated here are related to the load carrying capacity of the gear. So on the left hand side, as you can see, we have the general results, which includes the actual gear ratio of the calculation, the number of teeth, what is going to be the module, face width ratio, the base helix angle, and circular pitch. And on the right hand side, you can see the allowable bending stresses, safety factors, and the pitting stresses. So here, the design here uses two strength calculation methods. One is the bending stress that validates the design for bending stress only, and then the second one is bending and contact stress that validates the design for both bending and the pitting stress. And the last option is the calculated geometry. So this gives you a detailed description about the geometry of the pinion and the gear, such as the base diameter, the outside diameter, the pitch diameter, what is going to be the tooth thickness, and etc. So now let's take a look at how you can generate this spur gear in action inside Solid Edge. So this is a conveyor assembly that we'll be working on for the entire presentation here. And we'll be generating two gears on these two shafts right here. So let's try to hide the parts that we don't require. And for this specific example, I'm going to be using this box gear configuration. So like I mentioned, to access the engineering references, you can come to the Tools tab. And in the Tools tab, you have this engineering reference dropdown from where you can select any kind of parts that you want. If you want a spur gear, a bevel gear, a worm gear, rack and pinions, sprockets, maybe pulleys, and so on. So this is one way of accessing. The other way is if you come to the edge bar here, you have the engineering reference command right here, which gives you all the same options. So the way you turn on any specific designer is you simply double click on the icon. And this specific example, I've turned on the Spur gear designer. And as you can see, this is the same exact screen that you saw in the presentation slides, where you can specify the gear parameters such as pressure angle, helix, center distance, the direction, accuracy, and so on. So for this specific example, I'm going to be using a center distance of 203.2 mm. And for both my pinion and gear, I'll be using a same hole diameter of 42.88 mm. And the face width here is going to be 72 for both the gear and the pinion. And then you can specify speed, power, efficiency, etc. Now to assign the material, you can come to the material option and select the material from the list. So for both my gear and pinion, I'm going to be using the same material. And once you hit calculate, you're prompted to this calculated results, where you can see the results calculated based upon the specifications that you have entered. So based upon the specification that I have entered, the total number of teeth here are going to be 22. This is going to be the module. The circular pitch is 28.27, and these are the bending stresses for both my pinion and the gear. And the factor of safety, as you can see, is quite high. So I get a green light to go and create these gears. And in the calculated geometry, as you might have seen in the presentation, you can see the base diameters, the outside diameter, pitch diameter, the tooth thickness, etc. So now to create these as parts, you have to select this create option, and then it generates new parts for you. So then here you have to give these and say give these parts a name and save them. So here I'm just going to give it a simple name like gear and pinion. So once you save these two parts, they are placed in the assembly. Now, a really good part about using this Spur Gear Designer is that these parts are placed along with the relationships. So as you can see here, I have my face mates, the planar aligns, the gear specified, and the path specified as well. Sometimes you get some additional relationship. For this specific example, I don't need these, so I'm just going to remove them. Now, I don't want these gears to move around in the space anywhere they want, so I'm going to just make them into a rigid set. So I'll go here and specify these two gears as a rigid set. And now it makes my job easier when I'm trying to align the two parts exactly where I want. So here I can use axial align, and you'll see that since we have made them into a rigid set, they both will move together in a pair, specifying the exact same location so that there is no interference as well. Once you've specified that, you can specify the exact location on what face do you want these gears to be placed on. And then the last one is axial align. So once you fully define the location of these gears, you'll see that these gears are now fully defined and the rotation is locked. And one of the main reasons why the rotation is locked, because we have made them into a rigid set. So now since we no longer need that rigid set, you can simply go ahead and remove that. And now if you try to drag the gears and try to move them, these gears should move exactly the way you want without any interference. So it's as easy as that. Using a Spur Gear Designer along with the relationships, you can place a gear within no time. So that's the benefit of using the engineering reference. Now, one more thing that we want to do here is that we want to create a rigid relationship between the gear and the shaft here. But the problem with the shaft here is a part of a different subassembly. So what we'll have to do here is we'll have to move these two parts and transfer it to the top level assembly here so that they're in the same assembly level as the gear and pinion. Now, what I can do is I can go ahead and start creating a rigid relationship between the two. And now once you've specified that, what you can do is you can try to drag the component to see if the gears move along with the shaft. This is exactly what we wanted. So when I'm trying to move the gear, the shafts move along with that, which looks good. Now, one more thing that you can do is you can assign a speed to this gear. And that can be done using this rotational motor option. So the rotational motor here, the way this works is you specify the part which is going to be moving, which is going to be this gear, then specify the axis about which it is going to be rotating, and then specify the speed and flip the direction if you want. So once you create this, this creates a new group inside the Pathfinder that is called as rotational 1. Now to simulate this, you can use the simulate motor, and it automatically identifies the available motors. So in this specific example, I only have one rotational motor, so it identifies that. And then once you start playing, you'll see that the gears move along with the shaft. And this is how you can specify a motor and simulate on any rotating object. So now we'll take a look at one more example where instead of adding spur gears to the model, we'll try to add the pulleys here. So let me exit out of this one here. Now for this second example, I'll turn on some different configuration of this conveyor belt. And now as you can see here, I have these 4 locations where I can add the pulleys. Now first thing we'll have to make sure is that the belt size that follows the sketch matches the standard belt size. And the pulleys we are going to be placing is going to be placed with respect to this sketch. So in order to make sure that the sketch perimeter is equal to the standard belt size, we'll try to check that using some options in the sketching environment here. Now, if you take a look at the variables created for the sketch here, so not a single variable specifies the perimeter of the sketch, and it's not, and there's no easy way to calculate that using some regular math. But we have certain options which are going to help you to do that. For example, this option right here that says area under evaluate group. So now the way this works is if you select the area that you're trying to evaluate, it gives you an area attached to your cursor. And once you hit accept, all the variables with respect to that area will get added to the variable table. So for example, if you go to variables here now, you see a lot of different variables have been added. For example, here the area, and the one that we are interested in is going to be the area A65048 perimeter, which is going to be the length of the entire sketch, which is not a standard length. Now, to make sure that this matches the standard length, we'll be changing this variable right here. And we're not going to do that using some manual process, but we are going to use this option called as a goal seek. So where this goal seek works is you specify what your goal is. So my goal is to change the perimeter of this sketch. Now, if you select that, it automatically highlights the current value here, that is 954122. Now I'll change this to a standard size, let's say 10,000. And which variable I'm going to use to change that? That is the tensioner adjustment, which is this 1400 length. Once you hit accept, the software runs some iterations. And as you can see from the status bar here, we ran a total of 25 iterations. And then this is what the result we got. And now our the new perimeter is 10,000 mm.
Yeah.
So now if you go back to your main sketch, this is going to be the standard belt size. But one more thing here we'll have to make sure is that this assembly here, the head adjustment assembly, should be axial to the sketch. So then we can just simply apply an axial relationship to these two. And now the way this works is each time we change the length or the perimeter of the sketch, the head adjustable assembly should move with that. So let's take a look at that if it's working right. So I'll go back to my profile, and this time I'll change my goal seek option from 10,000 to 11,000. All the options still are going to be the same. So save that. And if I close this, you'll see that my head adjustment assembly moves with respect to sketch, and it is working as designed. Now to bring in pulleys, we'll do the same thing from the edge bar here. You can see this the solid edge pulley designer, and now this is very similar to what we did in Spur here, where you specify the design parameters. The software will give it the calculated results and the dimensions. So here you can specify what kind of groove do you want. You have the classic V and the narrow V. What section do you want for those? And the number of pulleys. So here we are constrained to either having 2 or 3 pulleys at a time. And how many belts you want for each of the pulley. So here we have the values all the way from 1 to 10. Here what I'm going to change is I'm going to change the mounting hole diameter from 10 to 28.58 for both the pulleys. And calculate that. So it looks like the strength validation has been passed, and we are good to go to create these. So this is going to be my pulley 1. And this one is going to be the pulley 2. So once you save that, it will be placed randomly inside the top level assembly, as you can see here. Now, one thing I did not specify, or I might have missed that, is to specify the distance between the two to make sure that it aligns exactly where we want. So to achieve that, what we can do is we can set one of the pulleys, and then either you can specify the distance from here, or you can simply remove that and just place the pulleys as they are. So here I'm just going to remove the distance and then place the pulleys with respect to the sketch here. So so first axle align the pulley over there, and then create a face mate with respect to the sketch. Same thing for the pulleys, it is already in line, so I just have to do one more thing, that is specify the axle align with respect to this pulley and the sketch over here. So you see how easily I have placed those two pulleys with respect to the sketch. And now you can do, we'll have to place 2 more pulleys. So now you can either go ahead and create those 2 pulleys again, or you can just simply bring in the existing part, because now you can use this part as a standard part now, and just bring those part in and assign the relations, the relationship to it. So axle align this hole with the circle, and then do a face mate on this face with respect to the circle over here. And then same thing we'll do again, bring in the same part, bring it in, and repeat the same process. So that's the benefit of using the engineering reference, that you can quickly create parts and use those parts as standard parts, like I mentioned. And now all you have to do is just create your belt, or bring in the belt that you have from your that you might have from the standard parts, and just place it here. Now the good thing about this is, since we are driving the perimeter of this entire model from the sketch, if we go ahead and update the sketch here, so let's say for example, if I go back again and use goal seek to change the value, so instead of 11,000 now I want to change this to 9,000. So if I do that here, my pulleys should get adjusted based upon the sketch. So as you can see, the pulleys have now adjusted with respect to the sketch, because when I created those pulleys and established that relationship, I've established the relationship with respect to the sketch. Okay, so now we'll take a look at one more most underutilized feature inside the software, and that is called as the 3D Finder, which gives you access to a huge number of standard parts from the manufacturer's catalog. So here, say for example, I have this frame here, and in this frame assembly, I want to clamp this frame member and this frame member over here with the help of these two supports. So now there's a specific part that I'm looking for that I know is available in the manufacturer's catalog. So what you can do is you can insert that part from the 3D Finder. So once you select that, this gives you access to the manufacturer catalog part files, and the part I'm looking for is a clamp. So if you search for clamp, the software gives you a random list of all the clamps available inside the software. Now I'm looking for a very specific supplier, that's reed supply. So you scroll down here in the suppliers list, and that is it is. So that's reed supply. And now for the specific supplier, I'm looking for a very specific part. That part number is TC331. So if you simply type that, you're basically narrowing down the search criteria. First you found out what the part was, then you found out which part number it is, and the manufacturer. And once you've done that, this is the part I'm looking for. Now I want a part that has a part that has a length of 7.5 inches. So if you look in this four variations, there is just one single part which has this one 7.5, and then I want a part which has in height of 2.89 inches, which is right here. So once you select that, you have two options. You can either download the CAD file locally, or you can simply do send this to the software, so it goes and places itself in the current assembly. Now, one more thing that we have here is on the right hand side, it gives you all the similar parts that are available inside this manufacturer's catalog with respect to this part as reference. So this part right here is 99.2% similar to this part over here. So it gives you a list of all the parts that are similar to this one. Now, once you do that, you can just select send to the software. And right now it is downloading. And the next step is it'll ask me which folder do you want to save this in. And then I can select the folder. It saves this part file over there, and it opens up inside the software. And this is the window you will see. So I'm just going to select my downloads folder to save that part, and this is the part that I'm looking for. So now once you have this part here, you can simply use the relationships to place that part in the assembly. So now in this specific instance, it's kind of easier for me to place this part. All I have to do is simply select face mate, flip the part here, and then select the axle line with respect to this part. So once you've placed that, this is how it looks. And that easily, by simply looking up inside the manufacturer's catalog, you can bring in the parts and place them inside the assembly. Now, say for example, if you had like multiple locations of this similar part, you don't have to reapply the relationships again. You can use features like capture fit or assign capture fit to let the software learn the relationships. And when you bring in the part, you can simply place it wherever you want. So say for example, now we'll take a look at the example of the capture fit. Now what I'll do is I'll select this assembly from the pathfinder and make the software learn the facemate and axle align relationship. So what happens is next time when I bring in the same part, the assembly knows the relationship, and you'll see this manage relationship window show up. Now I don't have to select the faces and holes on the part here. I simply have to select the faces on this frame, and then select the hole which I align to, and that easily I have placed part inside the software. So using 3D Finder will be of great help if you are able to find the parts that you generally use from the manufacturer's catalog. And then you can use features like assign capture fit or capture fit to place all those parts extremely easily inside the software. So that's all I had for today. Thank you for your time and attending this tech talk.